Okay, so we're going to go ahead and start our final lesson for midterm number 2. And this is going to deal with complex zeros and the fundamental theorem of algebra. Okay, so let's first start by looking at the fundamental theorem of algebra. So it says that every polynomial function of degree n greater than or equal to 1 has at least one complex zero. And a lot of times when we are looking at polynomial functions, the degree of our polynomial a lot of times determines how many complex zeros the polynomial function has. Okay, so if you have a fourth degree polynomial, a lot of times that fourth degree polynomial is going to have 4 complex zeros. Okay, let's talk about one other thing and then we'll get into some examples illustrating some of the stuff that we've talked about. So the next thing we're going to look at is the conjugate pairs theorem. And the conjugate pairs theorem says to let the function f of x be a polynomial function whose coefficients are real numbers. Okay, so if r, which is equal to a plus bi, is a complex zero of f, then r bar, so what we have r with the horizontal bar on top, which is the conjugate of r. Okay, and again, like we've worked with conjugates of complex numbers. Remember when we had like a complex number that looked like this? 3 plus 2i over 5 minus I. Like we had to multiply the numerator and denominator by the conjugate of the denominator in order to rationalize the denominator. Okay, so the conjugate of a complex number is one where the real part and the imaginary part of the number are the same. It's just the sign in between the real part and imaginary part is opposite. Okay, so if a plus bi is a complex zero of f, then its conjugate a minus bi is also a complex zero of f. Okay, let's do a couple of quick examples with this and then we'll get into some more complicated examples. All right, so directions here say that info is given about a polynomial function f of x whose coefficients are real numbers. And then we are asked to find the remaining zeros of f. Okay, so for problem number 1, we are told the degree of our polynomial is 3, and we are given 2 zeros for the polynomial. Okay, the first 0 is a real 0, being 3. The second one is a complex 0, 4 minus I. So the fact that this polynomial is of degree 3 means that we are going to have 3 complex zeros here. So 3 is the first one, which also happens to be a real 0. The second complex 0 is 4 minus I. And if 4 minus I is a 0, its conjugate, which is 4 plus I, is going to be a 0 as well. Okay, you guys give number 2 a try. So you're told there that the polynomial is of degree 6, and it has zeros 2, 2 plus I, negative 3 minus I, and 0. Go ahead and pause the video while you work on that. Okay, so here, the fact that the degree of our polynomial is 6 means that it's going to have 6 complex zeros. 2 of them are real, so the 0, which is 2, and the 0, which is 0, those are real numbers. We have a complex 0, 2 plus I, so its conjugate, 2 minus I is a 0, and we have the complex number negative 3 minus I, so its conjugate, negative 3 plus I, will be a 0 as well. Okay, so those are all 6 zeros of that polynomial function. Okay, let's move on to one that's a little bit more difficult. All right, so directions here ask us to form a polynomial f of x with real coefficients having the given degree and zeros. And for problem number 1, we are told the degree of our polynomial is 4, and we are told that this polynomial has zeros of 3 plus 2i and 4, and that 0 of 4 has a multiplicity of 2. All right, so let's go ahead and work through this one together. So the 1 0 that we know the polynomial has, but is not explicitly stated, is the conjugate of 3 plus 2i, which is 3 minus 2i. Okay, so if we know the zeros of our polynomial, that also tells us what the factors of our polynomial will be as well. Okay, so our function f of x, leave yourself a little bit of space because we're going to add something in just a second to the right of the equal sign. But if our polynomial has a 0 of 4 with multiplicity 2, then x minus that number 4. Again, multiplicity is determined by the exponent, so x minus 4 quantity squared has to be a factor. Okay, if 3 plus 2i is a 0, then x minus that 0, so x minus the quantity 3 plus 2i is going to be a factor. And if 3 minus 2i is a 0, then x minus the quantity 3 minus 2i is also going to be a factor. Now again, like I can, just like we did in our lesson on, I believe, graphing polynomial functions, I can multiply out front by a, and that's not going to affect the location of the zeros. However, I don't want to like multiply a in at the very end, so I'm going to go ahead and choose to make a equal 1. Okay, all right, so let's figure out what polynomial results whenever we like multiply all this stuff out. Okay, so x minus 4 quantity squared, that's like saying x minus 4 times x minus 4. So if we FOIL or distribute that out and combine like terms, that's going to give us x squared minus 8x plus 16. Okay, now when I look at multiplying out these two quantities, that's going to be extremely messy. Okay, so I'm going to teach you a little trick to make multiplying that out significantly easier. Okay, so first thing I'm going to do is I'm going to distribute the negative here across both sets of terms. Okay, so when I do that, that gives me x minus 3 minus 2i times x minus 3 plus 2i. Okay, once I've done that, I'm going to regroup the two quantities like so, where we have the quantity x minus 3 minus 2i times x minus 3 plus 2i. And when we do that, we have something of the form a minus b times a plus b. So if we recall earlier in the school year, when we take a minus b times a plus b and multiply that out and simplify, that gives us a squared minus b squared. it gives us the difference of two squares, which means that when I multiply those two things together, that's going to become x minus 3 squared minus the quantity 2i squared. Okay, so x minus 3 squared, that becomes x squared. Whenever I multiply and simplify, minus 6x plus 9 minus, when I square the quantity 2i, I have to apply that exponent to each factor. So 2 squared is 4, and I squared is I squared. We know that that's equivalent to negative 1. So this just becomes x squared minus 6x plus 9 plus 4. So that becomes x squared minus 6x plus 13. Okay, which we are multiplying by x squared minus 8x plus 16. Okay, so I want you guys to distribute from there, combine like terms, and then make sure that that polynomial is written in descending order. So go ahead and pause the video to do that. Once you're done, you can unpause the video and we'll work that through together. Okay, so when we go ahead and distribute, I'm going to take this polynomial here and distribute everything across this polynomial. Okay, I'm not going to draw arrows step by step. Like, we've practiced enough with this where we should have this down by now. So our function f of x, when I distribute x squared across everything, that gives me x to the 4th power minus 6x cubed plus 13x squared. Okay, when I distribute negative 8x across all three terms, we get negative 8x cubed plus 48x squared, and then negative 8x times positive 13 is negative 104x. And then lastly, I'm going to distribute 16 across all three terms. So 16 times x squared is 16x squared. 16 times negative 6x, that becomes negative 96x. And then 16 times 13 is positive 208. Okay, and then the last thing for me to do here is to combine like terms. So we get x to the 4th power. Here are my x cubed terms. So negative 6x cubed minus 8x cubed is minus 14x cubed. Here are my x squared terms. So 13 plus 48 is 61, and 61 and 16 is 77. Those are my x terms, so negative 104x minus 96x is negative 200x, and then my constant term is 208. Okay, and that right there is the polynomial of degree 4 that has those zeros. Okay, so I'll have a couple of other videos posted to continue the lesson from this section. Hope you guys have a great day.